and we'll continue with calmet from Sussex, who will talk about unitarity in quantum gravity and particle physics.
Thank you very much, Sabina, for the opportunity to present this work. So, if there's one message I would like you to remember after this talk, is that the scale at which gravity becomes strong could be much lower than naively expected. And that not just if you have more than four dimensions, but the particle content of a model can affect quite dramatically the scale at which gravity becomes strong. So here's the outline for this talk. I will first discuss the strength of gravity. Then we'll come to some more recent work where we try to see if there's an energy scale at which linearized gravity coupled to particle physics model people have discussed in the past would break down. And then we'll get to applications to models of low-scale quantum gravity that people have discussed as potential new physics models at the Large Hadron Collider. And I will discuss some of the implications for experiments at CERN. Then I'll come to the conclusions. So you all know that if we live in more than 4 dimensions, so that's Einstein's action more than 4 dimensions, the fundamental scale in the action m star could be around 1 TeV. But we could be tricked into thinking that the Planck mass is some huge number if there's a big volume Vn. Now, once you've realized that, you have different ways to implement this idea. One is a grain 1 model of ADD. You could have 2 grains, but it's roughly speaking the same idea. It's all because you have the same big volume. Now, the thing we got interested in a few years ago was whether you could get a similar effect in 4 dimensions. And for example, you just consider regular GR with a massive scalar field and ask yourself how this scalar field would affect the strength of gravity when you have 2 particles slowly moving, exchanging a graviton. Essentially, that means calculating a loop diagram where you have, for example, a scalar field propagating. Now, you can do that without breaking the symmetries of the problem using the heat-channel method, and that regulator preserves all the symmetry on the other hand. What you find is that the Planck mass, or the reduced Planck mass in the case, squared measured at some energy scale mu, is given by the one we measure in astrophysical measurement at large distances, zero energy squared, minus 1 over 96 pi squared, mu squared, we use the energy scale at which you do the measurement, and NL depends on the particle content you have in the model. So at one loop you find that NL is the number of scalar fields, real scalar field, plus the number of fermions, minus 4 times the number of spin 1 particles. Now, you could make the case, I won't get into these details, that if N is somehow large, the graviton loops themselves are suppressed by 1 over N, so there's hope to get these things actually to make sense in calculating theory. Okay, so that's one thing. The other question is, when does gravity become strong in that scenario? So you can estimate the one-loop correction coming from a graviton to itself. And you find that it typically goes as 1 over 16 pi squared. The energy over the Planck mass, reduced Planck mass at this energy squared. And gravity becomes strong if you are the scale mu star greater or equal to 4 pi times the Planck mass at the scale. So you're actually just requesting that the one-loop correction be of 4 to 1. Okay, so that's a criteria we'll use later on. Please keep that in mind. So basically the message is that Newton's constant is running. And when I actually started to think about that, I Googled Newton's constant runs, and that's what I found. So people had the idea before in different frameworks though. Okay, so how can we use that to make some interesting physics? So let's say we want gravity to become strong at 1 TeV, like it is the case in models with more than 4 dimensions. So you want Newton's constant, the reduced Planck mass you get around 1 TeV at 1 TeV. And the way to do that would be to have a large thin sector that only interacts gravitationally with us, And what you find is that it would take some ridiculously large amount of fields, something like 10 to 33 scalar fields of fermions to get the Planck mass at 1 TeV, to be 1 TeV. So I don't take that model too seriously, but it's interesting that you can reproduce a lot of the phenomenology of models with large dimensions within 4-dimensional models. Now, it's really bad taste to introduce so many new degrees of freedom, but that's actually comparable to what people are doing with more than 4 dimensions. That's the number of KK modes typically in those models. On top of that, you don't shout at cosmologists when they tell you that what we see is a small sector of the universe, and there's a bulk of things we don't see, a large sector, so one for particles in space. Now, things don't get worse for the cosmological constant problem. You're not solving anything, but if your hidden sectors are symmetric, you have a rating for G Newton, but no further contribution to the cosmological constant. Just a side remark. That's because spin 1/2 and spin 0 go the same way for G Newton. So in that sense, although ugly, it's a technical solution to the hierarchy problem of particle physics. Okay, so the common feature of all models that lower the Planck mass and potentially dramatically up to 1 TeV is that they have a lot of new particles in a game, whether it's in sector, the KK modes. And so I was concerned about whether there would be a bound on the size of a particle physics model we could couple to gravity. So the tool we're going to be using is that of unitarity. And it's one of the very few theoretical tools we have to check the consistency of a model. Essentially, the assumption that if it just follows some conservation of probability in quantum mechanics, there's nothing wild about it. And it tells you that an amplitude cannot grow too fast with energy. So I'm simplifying things slightly, but that's roughly the idea. So it's one of the only theoretical tools we have to try to guess the value, potential value of some of the constant or parameters of your model. Now, one of the reasons, and most great example, is that of the standard model without a Higgs. You can calculate W scattering through a Z boson, a photon, and a contact interaction. You see that if you don't put a Higgs in the model, phase break down around 1 TeV. And if you put a Higgs in the model, you get a bound on the Higgs mass, which is something like 790 GeV.
I'm not an expert on this subject, but I have always wondered how much are we tied with the notion that we can believe perturbation theory in this regime?
That's, okay. Maybe I should say a few words about that now, but I could also say it afterwards. So, basically, the idea is, if you do not put a Higgs, okay, something needs to fix unitarity, and the assumption that people make is that the weak interaction would become strongly coupled and fix unitarity. Does that answer your question?
No, well, I'm thinking on general grounds. If you have an Hermitian Hamiltonian, then
well, look, that's
unitarity should be
there's
preserved
a way,
in principle.
Okay, that's a different question.
Theory.
But the way I'm going to be using it is that I'm going to put myself in a framework where I know to evaluate the strengths of the interaction, and I will know whether the strength is good or not in that regime. Yeah. And then I will check. Okay, but generally speaking, I agree with you, but let's come back to that afterwards. Okay. So the model we'll be looking at is actually very simple. It's just general relativity with a scalar field, for example, that can be non-minimally coupled. There will be a bi-fermion and spin 1 particles. And we're going to be looking at GR, at linearized GR, as some effective field theory. And we want it to be at least valid up to the reduced Planck mass. Okay? So that's going to be the framework in which I'm going to put myself. So once you have that, you can start to take the particles of your model and scatter them off gravitons. And to make your life simpler, we're going to be looking at scattering of particles of one type to another type, so one scalar to another type of scalar, just to make sure that we only have S channels. We don't want to have T new channels that lead to further complications. And so you can compute basically all the possible scattering amplitudes with scalars, fermions, vector 2 scalars, fermions, vectors, and so on. What you get is a matrix like that, and I'm not expecting you to be able to see all the detail. The important thing is that you have two channels. One are the j equal 2 channel and j equal 0. That's all that appears to be stable. Now, you can rewrite the amplitudes in terms of what is called the partial waves. That's this decomposition. And you see that, so the j equals 0 and j equal 2 are the only two that appear in there. Now, unitarity tells you that the real part, the absolute value of the real part of aj should be smaller than 1/2. Okay? That's just from quantum mechanics. So you can apply this consideration to the j equal 2 partial wave, and diagonalizing this matrix I had before on the slide, you can apply to scattering of a state defined this way that mixes scalars, fermions, and vectors. It's a standard procedure. You do that as well in the standard model to increase the unitarity bound on the Higgs mass. What you find is that the A2 partial wave depends on the number of fields n. So where n is a third of the number of scalars plus the number of real vectors plus 4 times, so this is plus, not minus, like we had for the loop, times the number of vector fields. And it grows as S over the reduced Planck mass. So basically what you get is a bound on the energy at which unitarity is violated in that model. So this energy that we call E star has to be, is smaller than the Planck mass, the reduced Planck mass, times 160 pi over n. Now, if n is large, this number can be smaller than 1. So you can be forced into a regime where unitarity is violated below the reduced Planck mass. Yes?
Yes, can I draw another conclusion from that? Which is that if n can be pretty large and we don't run into a unitarity problem even over the Planck mass.
I'm having trouble hearing you.
Yeah, so if n is smaller than 160 pi, which is probably true for the standard model.
For the standard model, yes.
Yeah,
But
then we can draw another conclusion from this, which is we can go way over the Planck mass without running into.
okay, so let me address that question next slide. Okay. So the point is that, well, actually, it's coming in 2 slides. But let me answer your question then, right now. The value at which the energy scale at which gravity becomes strong depends on the content of the model.
Sure.
Now, you can, basically what I'm going to do now is some kind of RG improvement of this story. Okay, so I'm going to find that unitarity becomes, for some model, is violated below the reduced Planck mass, and I know that gravity is still weak at that scale, so there's nothing that can fix it, basically. It's not like in the weak interaction case, where you can argue, oh, my weak interaction becomes strongly coupled. So you have to check 2 scales and compare both scales. The scale at which you violate unitarity to the scale at which to the scale at which quantum gravity becomes strong. That's the punchline. Okay? So basically, so I've told you already the story. The Planck mass, the scale at which gravity becomes strong, depends on the particle contents. It's a different NL. For example, here we had a 4 for the other N. Now, to be conservative and be as friendly as possible to the model, I'm going to assume that gravity is only strong at mu star, not 4 pi, if you remember. So I'm giving a break to the model. I'm going to assume gravity actually becomes strong before it's actually supposed to. I'll find this scale mu star to be m squared, the reduced Planck mass squared, over 1 plus NL over 96 pi squared. Now, the criteria for the validity of the infinity theory is to compare E center of mass to mu star, as we were discussing a second ago. And E center of mass, once you actually improve it, is this relation. So you have the Planck mass that is now depending on the scale which you measure it. So you have 2 configurations possible. One where mu star is below the unitarity, the scale at which unitarity is violated and the theory is safe. On the other hand, if you find that gravity becomes strong above that scale, you're into trouble. So that gives you a bound basically on n. We find from the j equals 0 that n is, so this combination of fermions and vectors should be smaller than 160 pi. and you get a bound on the number of scalars from the j equals 0 partial wave. Now, how seriously should we take this? Now, in the weak interaction case, since you don't know, if you don't have a Higgs, you don't know the UV completion, you don't know how to really write a model. So you may argue that the weak interaction becomes strongly coupled. You don't know for sure. Okay, so there could be a factor. You don't know for sure at what scale. In this scale, in this case, things are more under control, which is surprising again because we're dealing with gravity, but we know the UV completion. So if you remember one of the first few slides, I told you that we expect perturbation theory to break down at a scale mu star, which is 4 pi times n bar of mu star, and actually consider just the weaker requirement that mu star should be observed n bar at mu star. So I'm giving a break to the model. Okay. On the other hand, unitarity we used, the quantum mechanical part, we only used that the real part of AJ, the absolute value of it actually should be 1/2, instead of, for example, taking much smaller than 1/2, which is something you could justify. So again, we were extending the validity of the model as much as we could. So the actual bound is probably much tighter than what I'm quoting here. Okay? So basically, if there's a factor 2, we already gave it away in favor of the model. Okay, so let's now discuss a few examples. As you guessed correctly, the standard model is fine. So you have 4 real scalar fields in the standard model, 45 fermions, 12 spin-1 particles, and you find that n is 283/3, so that's fine. In the minimal supersymmetric standard model, again, you find that you're fine. But some of the SUSY models people like have enough particles to get into troubles. So the non-SUSY SO10, for example, is fine with 10, 16, 45. It's a big representation already. But if you take a SUSY SO10 with some sizable representations, you find that you can violate that bound. In the model I've described to you to lower the scale from gravity to 1 TeV, clearly with 10 to 33 particles, you violate that bound. So what you find in that model, for example, is that unitarity is violated at 590 GeV, when you expect it to become strongly coupled at 1 TeV. So you need some kind of new physics to fix that. So this is just a list of particle physics model of unification that people have discussed and whether they pass the J equal 2 bound or the bound on the number of scalars. And you see that the more supersymmetric and the bigger representations you have, the tougher it gets to pass the bounds. You have more particles. So the minimal SU5 is fine, for example. Okay, so there's an interesting side result of our result for models where the Higgs boson is in inflaton. This has become quite popular again. It's a beautiful idea because that would be a way to unify 2 scalar field into 1. So they rely on a non-minimal coupling of the Higgs to the rich scalar. Now, from the J equals 0 partial wave, we get a bound on the minimal coupling. So for 4 degrees of freedom, like we have in the standard model, that's what you get for psi. You see that in this model, they had to pick psi to be of the order of 10 to the 4. That means you violate unitarity at 3.5 10 to 14 GeV, and gravity is expected to become strong at 10 to 17 GeV. So that's a problem for that model. Okay, so can we fix this unitarity problem? Yes, you can fix it. For example, if you embed these models into string theory, you could lower, if the string scales below the Planck mass, which is what you expect, you could fix it. Now, that's kind of interesting because if you think in terms of model building for the Large Hadron Collider, here it's not a choice, you have to do it. So if you're looking for strong gravity at the Large Hadron Collider, you should see some kind of non-local stringy effect before you see any gravitational physics. You could also potentially use these effects to extend the reach of the search for the Large Hadron Collider. Now, I'm going to tell you that the similar bounds apply also to model of large extra dimensions, so this comment applies there as well. Now, Tom had pointed out a few years ago, I think, that fixed point could improve the UV behavior if gravity somehow can be weaker in the UV. they parameterize that with a form factor. I mean, the problem, it's a beautiful idea, the problem is that it's actually tough to make real serious calculations in a non-quantitative regime. But again, at one loop, we don't see gravity becoming strong soon enough to fix things. Okay, so let me now tell you a little bit more about the non-minimal coupling of the scalar field to gravity. So this is the...
In your previous transparency, sorry for the...
No problem.
You assume that the volume there does not run with the scale, am I right? So you assume that your dimensions are stabilized.
Yes.
Because in general...
Well, but that's fine, because you treat it as an effective field theory.
Yeah.
And below 1 TeV, I'm allowed to write 10^32 kk modes.
That's all.
Okay, so that's essentially what you saw earlier, but now is included a piece that describes the contribution of the non-minimal coupling. And you can go to the same game again and look at what scale gravity becomes strong, and you see that it now depends on psi. You can get again the bound from j equals 2, which is not affected, but j equals 0 is affected. Now, this bound applies for n, so the number of scalars greater than 1. And that's interesting. So it applies for the Higgs case. That's what I used earlier. Now, you could build a model with just one lousy singlet scalar field. In that specific case, if you look at scalar scattering, there's a cancellation between the S, T, and U channel, and that's the amplitude. I'm not asking you to look at all the terms. What's interesting is to see that when you go to the higher G limit, so when you take the Mandelbrot parameters to be greater than some minimal S, you see that this object does not have terms that grow with energy that are proportional to the size of the mass. So there's no bound for a single scalar field. So that opens the door for two funny models. First of all, you could use this non-minimal coupling to replace the 10^32 particles by picking a large non-minimal coupling to get gravity strong at 1 TeV. But you could also play the other way and try to get gravity to get weaker in the UV by picking some more reasonable psi. Now, there's a big assumption here, namely that higher order terms, cos squared and so on, do not cancel out the effect. So that's not something we've checked. It's just an observation at this point of something that could be funny. Now, what can we learn from unitarity in that case? Well, you can go through exactly the same procedure. What you find is a bound on the mass of the scalar field. Excuse me. So for psi of the order of 10^32, you find that your scalar field, your single scalar field, has to be smaller than 10 to 14 GeV, which is not very good because that creates a lot of problems with cosmology. So, and we would have C modification of 1 over R potential also if you had a light scalar field propagating. So, what is the smallest value you can choose? Well, you can take psi to be of the order of 10 to 30. That's a mass of 10 to the -3 eV, which is for the scalar field, which is borderline of what has been excluded or not. But the thing which is amusing is that in that way you've lowered the Planck mass to 14 TeV, which is just borderline for the Large Hadron Collider. So what's amusing about this model is that this is a minimal way to reduce the Planck mass without having a unitarity problem below that scale. So that's what we can do. If you reduce it further, below 14 TeV, you end up with the need to include new physics. Okay, so we've checked something that I believe was well known, namely that if you look at graviton scattering on pure GR, there's no problem of unitarity below the reduced Planck mass. So those are just in the NC basis different amplitudes, and you see that the center of mass energy is smaller than square root of 8 pi times the reduced Planck mass. So there's been some activity recently in that direction by Giddings and collaborators arguing that solving the unitarity problem in gravity was actually more pressing than understanding how to normalize it. And I think it's an interesting development that should be looked further into. Okay, now let me come to models that people have discussed extensively in the last 10 to 15 years to study models of large two-dimension. Now, as I've shown you earlier, you relate the reduced Planck mass that you observe, you think you observe in astrophysics, to the fundamental scale of gravity ND and to the large volume. Now, typically what happens in that case is that you have a large number of copies of the graviton, the KK gravitons, and typically you have something like 10 to 32. I'll do things a little bit more precise in a second. Now you can look again at the scattering of all the particles of your model, so scalars, fermions, vectors, through KK gravitons. Now, the difference is that there's no J equals 0 amplitude, but it's exactly the same situation otherwise. What you can get is a bound using the same trick on the partial wave, and it depends on the number of KK mode, on the number of particles you have in the model. Thank you. And so basically, by construction, these models' gravity is expected to be stronger than 1 TeV, but you find that unitarity is violated at about half a TeV. So that's important for experimentalists. That means something needs to appear if those models are relevant to nature before you see strong gravitational physics. So, for example, stringy effects. Yes?
I suppose the logic would also be turned the other way around. Since everything was in linearized gravity, probably if you consider nonlinear effects, you might be, so it's not necessarily unitarity violated.
Okay, so what you're telling me is gravity becomes strong earlier than I think.
Yeah.
But that means it's a problem for the model, because by construction the model becomes strong at 1 TeV.
Right.
So I accept your comment, but in any case, yeah, well, okay, two ways to see that. Model is crap, forget it. Optimistic, there's something you, okay? I agree completely. I mean, actually, I would share your perspective more than me. Okay, so I could be accused of having been a bit too careless. So you can actually count the number of KK modes properly, cut off the number of KK modes you take accordingly to the energy when you stop. And well, that's what my student did. And you find that depending on the number of extra dimension, you find violation of unitarity at 0.47 up to 0.59 TeV. So even when you do things more carefully, there's a problem. Okay, so again, so the punchline is that the particle content of your model does depend very much, does matter very much for gravity. Vice versa, quantum gravity matters very much for particle physics models as well. One of the things that I've been talking about today is that in these gut models, these quantified models I was presenting to you, there are operators that can help to unify the forces of the standard model that are much more important than people thought because they're less suppressed. The Planck mass is lower than you think than before. And you can actually unify the standard model perfectly without supersymmetry. You can even shift the unification scale higher or lower. You have this freedom. So it's very dangerous to extrapolate from low energy left data without knowing what's happening with quantum gravity. So I hope I've convinced you that quantum gravity is important for models of particle physics, unified models, but also models that try to lower the Planck mass in the energy rich region. We found a bound on the amount of matter you can couple to GR, and if you still like models with large structural dimensions, that has deep implication for those models. You will see some sign of new physics that fixes unitarity before you see any new gravitational physics. And I hope I convinced you that gravity is still a fascinating paper. Thanks a lot.
Just a simple question. So your Planck mass was running as a function of the scale where you fix the
energy scale.
So it means that you have some kind of definition for what Planck mass is as some kind of scattering amplitude?
Well, think of it that way. So if you are at very, very long distances, low transfer momentum, that's the Planck mass emerging in astrophysics. When you go,
what is the process whose amplitude you look at to fix and
so think of it, two slowly moving particles that exchange graviton. That's the way you calculate in field theory one of R Newton potential.
Okay.
Okay. So you can ask yourself, how does this get renormalized when you have some particle propagating in the center of the diagram? So that's why this diagram essentially. If I find it. Okay,
So
so you have two slowly moving particles,
the wavy lines are
gravitons.
gravitons. So it's are you looking at the pole of the
So-
graviton propagator? or something?
No, all you have to do, frankly speaking, is quantum field theory curve space-time. It's just a heat kernel calculation.
Right.
So, actually, okay, I have backup slides if you want to see the details. I don't think I'll take all of you through that, but that's what you calculate, basically. The one with effective action. And that result has been known since the late 60s. Okay, so there's
Okay.
nothing new there.
Yeah.
It became very popular again in the 90s with work of calmet, Wilczek, Larsen. We're trying to understand the entropy of black holes, and that's where these calculations that we've done.
Okay, but this Planck mass, if it when it appears in Lagrange, it's 1 over Planck mass times the Ricci scalar. Is that where?
Well, okay, so you. Yeah, I mean, that's, yes, you start
Okay,
with
so that tells you that the propagator would be proportional to MB, and so you're using that.
so you look at how quantum corrections shift the. That's exactly what you do in QED when you calculate the running of alpha QED.
Right. Well, in alpha you have scattering process between.
Yeah.
Yeah.
Yes, exactly. That's what I'm saying. Yeah.
Okay. So. Right. Okay. I think I understand.
Yes.
Yeah. So while you're worrying about unitarity, is what you're doing equivalent to calculating a graviton propagator to leading more than 1 over n?
Okay. I'm worried about unitarity because when you start to. You have two questions, I think.
Let me ask my question.
Yeah.
Let me make a statement and then ask the question. Because there are several issues with unitarity. One of them you discussed is the increase of the scattering
Yes.
of energy. But there's another issue with unitarity. If you calculate the graviton propagator to leading order of 1 over n,
Right.
which you seem to have implicitly done to invoke the normalization group,
Yep.
then there's a pole at,
Yeah.
at piece.
So that's not the piece I'm worried about.
So why aren't you worried about that?
Because you can, okay, first of all, there's a regime where you would expect this correction to be small. And you would expect, that's what the whole work of Donahue. You can do calculations in quantum gravity, linearized quantum gravity results, and you get answers. There's a regime where you expect things to work.
So you're saying the issues you're worried about, you would see in energies before you see the
Yeah.
issue of the leeway.
Exactly, that's my understanding of this.
Excuse me, but my understanding is that except for factors of order 1, I believe that if you do the kind of analysis that you are talking about, the dependence on the Planck mass and n that you will get is exactly the same one that you got. And there will be factors of order 1 and pi. And
No, but the point is, look,
but
the
the
point
dependence on n and the Planck mass square and so on that you will get will be the same one when you do the kind of analysis that you're referring to.
That's my
You will
question.
get the
So
same kind of.
there's a regime where you expect to be able to describe gravity with the exchange of gravitons without getting into trouble. If you're below the reduced Planck mass, for sure, up to 4 pi times the Planck mass, you expect the theory to be, in a sense, classical.
Well, so the question is, are you working consistently to order 1 over n or not? Because if you're working consistently to order
So-
1 over n, there's not just the exchange. of
So you will
gravitons,
get,
there's the infinite
okay,
diagram.
you can try to make the case, and I don't have a proof, that all these diagrams with the, you have to look at higher loops, okay, with all this n, and I actually thought that your work would motivate those things. You could actually have a consistent 1 over n expansion, and resum all these diagrams. That's something I'd be happy to talk to you about.
Okay, maybe it's too technical. Let's
Yeah.
talk about it.
But my suspicion is that there's a well-defined 1 over n expansion in that game, and that things are under control. But the whole thing is at one group at this level.
I had a much simpler question. Maybe I did not follow the details when you were talking about some of these grand unification models that were ruled out.
Well, you would know that something funny happens there. Yeah.
Right, and so I was just trying to understand because it seemed that the number of particles that you were having in some of these SO10 or so
Yeah.
was of order, I don't know, a 1,000 or maybe even 10,000.
Yeah,
I was
I mean,
trying to understand because roughly the order of n that you are getting sort of generated, or maybe even the previous slide that you had before that one.
so
Because roughly the numbers that you get before getting into this more detail is of order 10 to 30 or things like that. So how come an n of order 1,000?
No, I mean,
is
what-
Susi SO10? No, what is the
I
name
think
that you
you're
have?
getting confused. So that there are different type of models. Okay, in those models, gravity does not become strong at 1 keV. Those are just models people discuss on a daily basis,
Also, okay.
and then
because,
cross check whether they pass the bounds or not.
okay. So here is because the scale here is 10 to 16.
So
GeV
gravity,
or something
so
like that.
roughly speaking, gravity will become strong at square root of that number.
Okay. So the point is that the
I mean,
energy.
one was square root of that number.
So the energy scale where gravity is supposed to get strong here is 10 to 16 GeV or something like that.
Yeah, something like that. And that actually can be very important when you try to unify things, because you have higher dimensional operators of dimension 5 that are much more relevant than people assumed. So that's the game we played, and you can actually show that you have much more freedom to unify things.
Generically, one looks for large effects that are prominent at very high energies, but shouldn't we look also at the high precision, low energy experiments? And by that, I'm thinking about what do we know about the ranges of scale over which G has been measured? For example, Cavendish versus gravitational radiation by the binary pulsar.
Usually
What
pulsar
n
have-
you would need to have a change in G that has been measured very accurately at both regimes? That is, you know.
Well, I mean, with probe gravity up to distances of 10 to minus 3 eV, roughly speaking, in that level R, right? I mean, that may have been improved a little bit by now. I don't have the actual.
All right, but we have to make the point is that we have
Yeah.
two measurements
So-
at one and another.
Yeah, I mean,
If it
for
changes-
particle physics, the other one would be extremely local, right? If you had a modification in the infrared, I guess what you're trying to.
Right, but you know how the dependence is, right? It goes like mu squared.
Yeah, but that thing is, I would not trust this calculation in the other direction.
Mm.
Okay, that it's an argument. You go into the higher energy regime. So there are attempts in the by Reuter.
What says the lower scale over which you would trust the argument? What sets the lower scale
Well,
over which you would
okay,
trust the
Frank,
argument?
my naive understanding of that would be if I'm the infrared, so classical physics, I don't have any quantum correction, but loosely speaking, the Planck mass is just what it is. Now, if you have a correction, that's something like extremely non-local. Now, the only thing in that direction I'm aware of are works by Reuter using some exact normalization to approach where he was trying to take dark matter using some non-local effect of this type. But that's not something we see with this kind of physics. But there are attempts also based on RG arguments, as I said. But you will not see that doing a one-look calculation.
So this is a comment which is not very important. In fact, you were maybe was sort of implicit in your slides. But so when you were mentioning this connection between these models with an extremely large number of fields and models with extra dimensions, and in particular with this Randall syndrome and this close similarity. In fact, this has been discussed by people. The fact that you can use the ADS-CFT conjecture to, in fact, very precisely establish this connection. In this case, the Randall syndrome model with, let's say, one grain.
Yeah, you have to
And
be.
if you consider, the ADS-CFT conjecture, where you actually have at a finite distance, you don't really go all the way to an infinite distance, the boundary at a finite distance, so that you actually have a conformal field theory with a finite UV cutoff. Then actually you can see this connection between this model with, let's say,
Sorry, I missed the first part. Between which model? So RS and.
Randall syndrome, let's say, with with just one brain.
Yeah.
And then you use the ADS-CFT correspondence, but in this case you actually have the boundary at a finite distance,
Okay.
so that it would the correspondence will be with a conformal field theory, but with an ultraviolet cutoff, a finite UV cutoff.
Yeah.
And then the point is that you have this correspondence between this Randall syndrome model with one brain,
Yeah.
okay, with this extra dimension. So you have this large extra dimension model, and then you have this other model which is effectively four-dimensional, living on this. So a four-dimensional model with a large number of with a conformal field theory with a large number of fields and a UV cut, which is giving you somehow
Well,
this
you see that
correspond
I was trying to do
the
something
time mass.
in that direction.
And then they can actually, this has sort of been discussed. You can have this
Okay, let me ask you a question.
correspondence between the two and see that the two are sort of connected.
But let me ask you a question, because the closest thing I came to was to take ADD with 10 to 32 kk modes of the graviton. And I naively thought, okay, I could look at the RG of Newton's constant, taking account its 10 to 32 kk modes, and I should find a matching to 1 TV. Now the problem is that these kk modes don't couple minimally.
So this is quite different.
So how does this work? You have
so this is quite different. I mean, I'm not an expert on this, but this is quite different because this is really not Kaluza-Klein modes. This is in this context of ADS-CFT. So these fields are not Kaluza-Klein modes.
But it must be a low energy way of thinking of that. And that must, but I couldn't make it work. So if you have an idea, the very
well, we can talk about that later, and I can maybe mention some of the references. So these really correspond to these strongly coupled fields of this conformal field theory with strongly coupled fields, a large number of them. So it's not really Kaluza-Klein modes that you should be thinking about.
Let's talk about that.
To get the 590 GeV number here,
Yep.
for example, in the case of your calculation for Suzy SO10, you really assumed all these scalars are massless, right? I mean, you're even worried about the fact that they're 10 to the 14 or 15, or 16 GeV guys, so they should decouple from the loop?
No, because in the Suzy SO10 case, all the scalars are the same masses. So you do the calculation and still...
All 10 to the 16.
Yeah. So that all of them are
So
there.
they don't contribute to the loop until you get to the
Yeah, exactly. Yeah. But that's a two-loop effect that we see these things on... At one loop, there's just one mass. Sorry. Over my time.
So, if there are no more questions, then let's thank Sally again.